Okay, let us start. Welcome to Statistics and Data Analysis section. And our speaker is Stefanie Jegelka. She will speak about graph neural network and their use in machine learning. Please, Stefanie.
Thank you. So in today's lecture, I want to summarize some of the emerging theory for graph neural networks, one of the recently very popular machine learning models for learning on graphs. And this talk is really focused on ideas and strategies for approaching even an analysis rather than giving fine-grained detailed results. But let me start with recalling what machine learning is all about. So think of regression or curve fitting. So we're typically assuming that we're given so-called training data from an underlying distribution P, which consists of X, data points X and labels Y. And we're trying to learn a relationship between X and Y by selecting a function from a function class of parameterized functions with parameters theta. So what we want at the end of the day is not only fit those training data points, but we want to fit essentially all data points that we may observe from that same underlying distribution. So we measure this via the so-called population risk, the expected loss over that distribution. And the loss measures the divergence between the predictions f of x and the true labels y, or the observed labels y. So this could be, for example, a squared loss. Now, the tricky thing with that is that we don't know typically the underlying distribution P. So what we have to work with is the empirical estimate of the population risk, the empirical risk. So the way we are getting this function estimate is typically by minimizing this empirical risk. And now the big question is, of course, well, if we have this particular estimate, this f hat, how well does it actually do in terms of generalization? And that depends on, well, what kind of f do we actually get when we do this estimation? And that is affected by a few different factors. For example, first, the expressive power of our function family, what kinds of functions can I even approximate with it? And then the learning part, meaning the optimization and estimation. Often this empirical risk is non-convex and we are working with a small finite set of data. So everything is just estimated. So these are all factors that are coming in understanding the generalization of these models. And in this talk, we'll touch upon both the expressive power and the learning part. Now, I want to make this a little bit more difficult by not thinking about regression with vectorial data, but by thinking about regression over graphs. So the inputs are actually graphs and we are learning function over graphs. Now, this has several different applications in science and industry. One of the motivating applications was property prediction in molecules for drug design and materials design. Or you may have used Google Maps. It uses a graph neural network to estimate the travel times. You may also be predicting links in networks for example, drug interactions or recommender systems. Or your input is actually not really a graph, but a configuration of points, like a set of particles. And you want to forecast how that physical system evolves. So you can represent this as a graph as well. Or a bit less mainstream, predicting coefficients of Castano-Lustig polynomials. So let's make this a little bit more formal. So our input here consists of an attributed graph, a finite bounded graph, where each node comes with a vector of node attributes, and maybe we have some vector valued edge weights too. And what we are looking for is a function from this graph that embeds or represents this graph in a vector space, typically some RD, or each node, so a function on each node. So this output could be the label, or it could be some embedding or representation of that graph for some downstream application. Now, what do we want from such a function over graphs? So our first constraint is that it's a graph invariant. And that means that typically we may be representing that graph via an adjacency matrix. We are putting those node attributes into a matrix. And if we are permuting these matrices in the same way, well, then the function value shouldn't change because it's the same graph. So we want permutation invariance for that graph function and permutation equivariance for the node function, which means if I permute the inputs, the outputs should be permuted accordingly. So graph neural networks are really an instance of neural network with invariances or symmetries built in. So here's the outline for the rest of my talk. First, we'll talk about what is actually a graph neural network and define one. And then I want to think a little bit about what kinds of functions we can approximate with these graph neural networks. And then we'll go one step further and talk about the learning part, the generalization, both on new data from the same distribution and different distributions. But let's start with what is a graph neural network. And graph neural networks really have many origins and relations. I said some of the origins are in designing representations for molecules, including recurrent neural networks where they were first introduced as contraction operators, graph signal processing and graph convolutions, or also message passing in graphical models, etc. And they are an instance of the geometric deep learning framework where we are encoding symmetries and invariances via specific operations such as pooling and convolutions in machine learning models. So let me introduce to you one of the most popular, or probably the most popular class of graph neural networks, and these are message passing neural networks. They proceed in two main steps. First, we compute an encoding or embedding for each node neighborhood. Let's call this HV. And then we collect all the embeddings of all the nodes and we compute a so-called graph embedding via a so-called readout function. So this readout function is just a multiset function over vectors. That means it has to be also permutation invariant. So we'll soon see how you can parameterize such a multiset function. So let's focus on the first step where these also come up and see how we can actually compute these node embeddings. And this is typically done via message passing operations. So we go in round and each node maintains a representation HV. And it updates in each round its representation as a function of the neighbor's representation. So we have this aggregation step first, where it collects the representations of the neighbors, encodes them in one single vector, and then uses that to update its own representation. So here we see analogies to convolutional neural networks, where we apply a local filter, the same filter for each node in a local neighborhood, and we share that filter across all nodes. So here we are sharing the aggregation and update functions. So what is this aggregation function? Here is a common way to parameterize it, is that we have a nonlinear function phi from vectors to vectors that acts on each neighbor representation individually, then we are summing up the result. So the sum is a so-called pooling operation. I could use a maximum or some other invariant operation instead. That would also work. Now, what we have to parameterize is this update function and this phi function. Both of them are nonlinear function from vectors to vectors, or pairs of vectors to vectors. And we typically parameterize them via fully connected standard neural networks. And that's where the parameters, the learnable parameters of the model actually are sitting. And now if these neural networks are large enough and the inner dimension, meaning the output dimension of the FNN1 is large enough, at least the size, the degree of the graph, then I can have a universal approximator of all aggregation, all multiset functions. So let me briefly recall what is the fully connected network. So how do I parameterize these nonlinear functions? So the way a fully connected neural network works is it goes in layers, and each layer consists of a linear function parameterized by this matrix W and an offset vector B. And then we apply a coordinate-wise nonlinearity, for example, a sigmoid function, or for the purposes of this talk, the rectified linear unit, the ReLU function, which is piecewise linear. And then we just concatenate those layers. And it is well known that if the neural network is wide enough, meaning the layer is large enough, then we can, or the network is deep enough, then we have a universal function approximator of continuous functions. So going back to our message passing graph neural network, in summary, what it does is it goes in these rounds. It's a parameterized message passing algorithm, and it updates the node representations via these aggregate and update functions. We can equivalently represent this via a so-called computation tree, where we see that the red node V gets input from its neighbors, the blue nodes, and processes this via an aggregation function. So here I club the aggregate and update together in this gray box. So we get the specific computational structure of this network. The actual connectivity depends on the input graph, but it's predetermined. And what we are learning is the parameters of these aggregation operations, the learnable blocks. So now that we know what is a graph neural network, let me talk a little bit about what kinds of functions can I approximate with these kinds of graph neural networks. And this really boils down to the question, what kinds of graphs can a graph neural network actually distinguish? So what do I mean by that? I mean that, let's say I have two different graphs, G and G prime, and I compute the output of the neural network F for both of these. Is it the same or different? If it's different, I say the network distinguishes these graphs. And now this gives me equivalence classes. If I take this G and G prime and none of my GNNs can distinguish them, then they have to have the same labels or outputs everywhere. So I get these equivalence classes. And now to each equivalence class, I can pretty much assign an arbitrary value by the power of my neural networks inside. And all I have to preserve basically is these equivalence classes. So that also implies that any invariant function on the graphs, permutation invariant function, I mean here, that respects these equivalence classes, meaning it doesn't assign different values to graphs within an equivalence class, I can uniformly approximate that. So this relationship between distinction and approximation follows from a symmetric version of the Stone-Weierstrass theorem. But so basically what this also means is that now what we have to think about is, well, what kinds of graphs can these graph neural networks actually distinguish? What is the discriminative power? Or in other words, well, how does my graph neural network actually see a graph? It sees it as this collection of local neighborhood encodings, of these local computation trees. How good a representation is that to distinguish graphs? And this is actually a very well-studied problem. There's a lot of work in understanding this because it relates to the color refinement algorithm, or equivalently, the one-dimensional Weisfeiler-Leman algorithm. So what does color refinement do? It starts with an assignment of each node to a symbol in an alphabet, a color, and then it iteratively updates the colors of each node in parallel by uniquely encoding the colors in the neighborhood of that node. And so this is what the hash function says here. And then you can iterate this process until it converges. And once it converges, you can compare the set of colors for two graphs. If they are different, then the graphs are different. The other direction doesn't actually hold, unfortunately. So it's not a perfect isomorphism test. And now, as you may have guessed, if we just put our graph neural network update operation next to this, we see that it looks the same. It has the same structure. And we can simulate the color refinement algorithm if our update and aggregation function mimic this hash function, meaning they are injective. And here we are only replacing the colors by continuous vectors. That's the only difference. So this has two implications. The first one is that, well, if the color refinement algorithm cannot distinguish two graphs, no graph neural network, no message passing GNN will be able to do that, whatever parameters you choose, because of that equivalence. The second part is that it's actually really equivalent in the sense that if we choose a maximum graph size n, we can find and define a GNN that has these injective update and aggregation functions that is really equivalent in its expressive power to the color refinement algorithm. So we get this direct analogy, and that gives us a lot of implications. It tells us, for example, that we can essentially inherit all the results that we have about understanding the Weisfeiler-Leman and color refinement algorithms, about when they work and when they do not work. In particular, that they work if you look at if you're randomly sampling graphs, the failure probability goes to 0 as the size of the graph goes to infinity. We also inherit characterizations via logics with counting. That means logics where we have this counting quantifier, and the binary relations relate to the edges in the graph. So what kinds of queries can we express? So there's a lot of good things about this, but there's also drawbacks, and that is that we also inherit all the failure cases, which result from symmetries in the graph, from automorphisms in the graph. So for example, in general, this color refinement algorithm cannot distinguish graphs that have different sizes of cycles if you have enough symmetries. So you cannot identify subgraphs, identify cycles of a certain size, compute diameters, etc. So lots of structural properties you can actually not compute. And this is an issue in some applications, such as encodings for predictions for molecules, where, for example, you're looking at predicting something about the functionality of this molecule, and that depends on functional groups. And these functional groups are specific subgraph structures. So this is indeed a drawback. So because of that, people have thought about, well, improving discriminative power of these message passing graph neural networks. And there's a few different directions. First, instead of doing message passing on nodes, you can do message passing on k-tuples of nodes. This is analogous to the higher order versions of the Weisfeiler-Leman algorithm. Or you can try to break the automorphisms in the graph, those symmetries that cause trouble, by introducing node identifiers, or by augmenting the node attributes with additional structural information, for example, so maybe spectral information. Another approach is to just generally look at this scheme of encoding subgraphs and aggregating those results and choosing the subgraphs differently in different ways. So this relates to the graph reconstruction conjecture. So all of these improve the results both in theory and in practice. So the plot here shows the practical part. So we don't have time to talk about all of them. Let's talk about the first two a little bit. The first idea was, well, instead of doing message passing on nodes, let's do message passing on k-tuples of nodes. So this means our input is now a kth order tensor, and we get the additional dimension because of the dimension of the input node attributes, or attributes of these tuples. And then we can get graph neural network equivalents of the higher dimensional Weisfeiler-Leman algorithms. There's different ones, and we can get it for all of them. A somewhat related idea is to implement message passing on simplicial complexes. And then we can go one step further and say, well, why do we even need to do message passing? All we really want to do in an abstract level is that we want some equivariant functions on our node representations. And then if we want a graph representation, we just need an invariant pooling function in the end. So hence, what we could do is we could just parameterize directly equivariant operations. And for example, equivariant linear operations interleaved with these coordinate-wise nonlinearities, like the ReLU functions we had in the fully connected network. And then we just learn that directly. So that is also possible. Both of these approaches have similar equivalences to the k-dimensional Weisfeiler-Leman algorithm. The actual k or k+1 depends on the type of Weisfeiler-Leman algorithm you're mimicking, and to logic. So this is good. That means with every increased k, we increase the power, the expressive power. But it does have drawbacks because it's computationally expensive. So the computational complexity grows with the order k of that tuple that we're looking at. So it's very expensive for higher k. So here's another idea. And this is to think about, well, where do the failure cases of Weisfeiler-Leman actually come from in this case? So it comes from symmetries in the graph. So if you look at this little picture on the right, these are two different graphs with a different structure, and the two nodes with the arrow have the same local neighborhood structure, the same computation tree. Not really structure, but the tree is the same. And the problem really is that we do not know whether we have once gone around that 3 cycle or we have a red colored neighbor 3 hops away. So we don't know where the message came from. And this could be fixed if we would introduce unique node identifiers. Then we don't have that problem anymore. So if we do this, we get direct analogies to distributed algorithms. So local algorithms are distributed algorithms that work in a network where each node is a processor essentially, and they're exchanging messages, bounded size messages along the edges, and they're jointly computing something. So now we can study what they can compute, how many rounds they have to go, it's a fixed number of rounds, and what's the size of the messages. So via this analogy, you see the analogy to our graph neural networks, they're called message passing. We get approximation bounds for combinatorial problems that GNNs could compute, so the approximation algorithms. We get that GNNs could, in the best case, even compute any Turing computable function, including graph isomorphism. And we also get lower bounds on the number of iterations of our graph neural network and the inner dimensions of the representations that's related to the size of the messages. So we get bounds on the product or the t times root, the dimension, bounded by the size of the graph over log n or root n over log n for combinatorial decision, optimization decision problems. So that's pretty good. What's the catch? And the catch is that once we assign unique node IDs, we lose permutation invariance. Otherwise, if we permute the graph input, the input graph, well, we have to permute the node IDs the same way. Or otherwise we lose permutation invariance. So that means we know the permutation, that means we know graph isomorphism. So how could we solve that? One idea would be to say, well, I make these node IDs random. I draw them from the same distribution for each node. So they are different with high probability, but now we have random outputs. And however, if the outputs for the different nodes are distinguishable enough, even though they're random variables, maybe I can actually still gain from it. And that is actually the case. So we obtain high probability universal approximation results for invariant graph functions with random node IDs. This was a short overview of some of the approximation results that we have for graph neural networks to date. And in the second part of my talk, I want to think a little bit about, well, a graph neural network may be able to represent a function, but are we actually going to be able to still learn that function just by looking at data? So this is the question of generalization. And we will first look at generalization by saying I have my function estimated the parameters of my message passing network. Now I get a new data point from the same distribution. How well am I expecting to do? And in the last part of my talk, I will go one step further and make this even more difficult and say, what if that new data point is actually from a different distribution? Maybe this is a graph that looks much larger than anything that I have seen in my training data. So what would my neural network actually do? So let's start with generalization. So understanding generalization in neural networks is actually a challenging question. And the reason is that we are typically looking at a very high dimensional space and a very expressive model that can approximate a lot of functions. So now we are looking at our finite data set. We are minimizing this empirical risk. And we are looking, well, what is the population risk for that? So in principle, so we are looking at a regime where we can often just exactly interpolate our data points. So in principle, there's lots of different interpolations we could obtain, we could get from this neural network. So it's very hard to say what would be actually the population risk for this, unless we have a lot of data. So yet, if we look in practice, this interpolation is not arbitrary. And what this means is there's something else than just the smoothness of the functions that plays a role here, that limits the amount of data that we actually need to get a good estimate. And what is really happening is that there's other inductive biases. So for example, this empirical risk is typically a non-convex function for neural networks. So we initialize it somewhere, and the initialization is actually has a specific distribution typically. So the parameters that I'm choosing have a specific Gaussian distribution. And then I'm using gradient-based methods like stochastic gradient descent or gradient descent to optimize this. So the stationary point that I'm getting to is not completely arbitrary. Second, in some neural networks, like the graph neural networks, we are encoding symmetries, like invariance, equivariance, and they reduce the actual degrees of freedoms of my estimation problem. So there's some nice recent works on understanding how much you actually gain in sample complexity by including the symmetries, because you have some invariant function. And finally, related to the symmetries is the computational structure of this neural network that also plays a role. That means the actual sparsity of the connections, what feeds into what, etc. So all of these play a role here. So what has been done for graph neural networks? So the first set of approaches has looked at the complexity of the function class f theta more generally. And this uses classical approaches from learning theory, like VC dimension, like Rademacher complexity, etc. So it doesn't yet include anything about the optimization procedure, etc. It just looks at, okay, we have a certain type of functions and how complex is that. Second, we could include the optimization process, and that's a difficult thing. I'll talk a little bit about this, for example, via the neural tangent kernel framework. And finally, we could also look at the computational structure of the network and relate it to the computational structure of the task. So this is especially relevant if you're looking at learnable algorithms, for example, which is a recently popular theme in machine learning and optimization. So let me look a little bit about the second two approaches, because we have only finite time. So the first challenge was, well, how would I even include this optimization procedure? Can I somehow get an understanding of, when I minimize my empirical risk, where will I end up to? What kind of solution will I actually get? And the challenge is, as I said, is that it's a very high dimensional non-convex optimization problem. Now it turns out this high dimensionality actually, it becomes easier if we make it even higher dimensional. So if we give the neural network even more parameters, in this case, what we are doing is we are making the layers even larger, so even wider. We don't make it deeper, we make it wider. So we let the width of the neural network go to infinity, and at the same time, we make the steps of our gradient descent, so in this case, we're looking at gradient descent, infinitesimally small, so we're looking at gradient flow. So what happens in this case? What becomes simpler? Well, if you look at the optimization dynamics in this case, the gradients remain relatively stable. And then in that case, this optimization process resembles the optimization of kernel regression. So what does that mean? What is kernel regression? So kernel regression has an associated map of the data into some high dimensional space. And then it looks essentially at linear regression in this high dimensional space after applying this map. So here the map we are applying is this gradient map that I have on the slide. And the nice thing is that now we have a very good understanding about what kinds of solutions we are obtaining if we do gradient descent optimization in this case. So what we are obtaining has actually a nice form. It's a minimum norm interpolation. So we get a minimum norm function in the corresponding Hilbert space that corresponds to the kernel that corresponds to this particular nonlinear map. So in this case, this kernel is the inner product of these gradients. So we know we are getting this nice minimum norm interpolation, and we also have a pretty good understanding from the learning theory side about kernel methods. So we can apply, for example, a classical generalization bound for kernels, and this is what it would look like. So the generalization, so the population risk decreases, of course, with n, and it depends on some product of the label vector y and this kernel matrix H. So H is the inner product matrix after that nonlinear map. And so what this is looking at is how well does the structure of the labels match the structure, the geometry of the data, essentially. And this holds with probability 1 minus delta. That's where the delta comes from. So now we still have to show that this is actually a bounded thing, this bound, and we can bound this as a polynomially, for example, in the case of graph neural networks, if the labels y are generated by something that looks like one iteration of message passing with a polynomial aggregation function. So really by one step of this aggregation. So why one step? Typically, the neural tangent kernel is much easier if we look at shallow networks, because if we look at a Gaussian initialization and a shallow network, we get a nice closed form of what this kernel actually looks like. So there's two take-home messages here. The first one is that, well, if we make these simplifications of width going to infinity, we are looking at gradient flow and the Gaussian initialization. What we are obtaining tends to some nice minimum norm interpolation, so we can understand what solution we're actually getting. The second thing is that looking at what the solution we are getting, this gives us nice bounds if the structure of the underlying function that generates the labels relates to the structure of our neural network model. They are somehow similar. There's some structural correspondence. So this is something I would like to take a little bit further in the second part of the last part of my talk. So this is the idea of computational structure. And this is something that to practitioners is very well known. If we have various different types of inputs like language or images or so, we are typically not using a fully connected network. So for images, so for all of these, we are putting in some prior knowledge about the target functions that we are actually trying to learn. So for example, for images, we would use convolutional networks that encode translation invariance. For the lower two tasks, like physical reasoning, forecasting, simulations of particles and n-body systems, or trying to learn graph algorithms, such as I get a graph and I'm trying to learn what is the shortest path in this graph and output that. For those kinds of tasks, graph neural networks work really well. Even though the fully connected network in principle can imitate all of these things. So there's something about what prior knowledge we put into the architecture design of this neural network that makes it work better. So there's, of course, a different connectivity. There's invariances that we're encoding. So the question is, can we make this a little bit more formal and understand that relationship? So one idea that has been brought forward is this idea of algorithmic alignment. So if we look at our graph neural network as a running example, and I showed you that computation tree, it looks like a structured arrangement where I said the structure is predefined, the connections of some learnable modules. So the learnable modules are these fully connected networks in our aggregation and update functions. And now I can look at this computational structure and put it next to some underlying function that generated our labels. So for example, if I look at the Bellman-Ford algorithm to compute shortest path, what it does is it's a dynamic program. It maintains a state for each node and in each iteration it updates that state. If you look at the n-body systems, you have some, say, planets, and we have masses and velocities, etc., or particles. The next location of a particle depends on the locations and masses and velocities of these other particles. So it's more of a pairwise relationships, and it can be phrased in this dynamic programming framework that the next state of my node or item is a simple function of the states of the other items at the current state. And now you see that if my learnable parts of my graph neural network could mimic this dynamic programming update, then I have approximated this dynamic program. And now would that relate to sample complexity? Well, how complicated is that part that I actually have to learn? It's that DP update. And this motivates this idea of alignment. We can quantify this alignment by looking at how complicated would be that those learnable blocks that we would have to learn. So here, the update and aggregation functions, what would be the sample complexity of that red block to mimic the DP update? And then we sum the complexities of all of these. So, and if they are low, presumably that would help us in the sample complexity of the full model. And this is indeed what people have observed in practice. In theory, we have some initial support. If you have some intermediate feedback in the layers of the network, then you can directly relate the complexity of these learnable blocks to the complexity of the full network. And remember, these blocks are shared, so there's actually not that many of them typically. And so this alignment has guided many of the practical architectures that people are using, and we're trying to gain a theoretical understanding of basically theoretical foundations for why this actually works much better. But what I want to keep here is this idea of looking at the neural network as some fixed arrangement of some learnable blocks. And now we are looking at the blocks and trying to use that to tell us something about the behavior of the full network. So we'll use this again in a minute. So the past few slides were about looking at generalization, where the training and the test data come from the same distribution. In the last few minutes of my talk, what I want to look at is an even more challenging scenario, and that is, what if the training and test data come from different distributions? So what this means here, for example, is that I'm training on small graphs and I'm looking at larger graphs. If you are learning a shortest path algorithm on small graphs, you would expect that it generalizes to larger graphs as well, or graphs with different degrees, etc., different edge weights. Same as if you look at physical systems, if you're now looking at more items in your system, or you're looking at different masses, etc., you'd assume it's the same. But this is actually data that looks different, so it's even outside the support of your training distribution in this case. And so if you're looking at the analogy with regression, this is the setup, that I'm looking at training data in a small bounded domain, and it's very easy to approximate that function, or feasible. And then I'm asking the model, well, what should be the value at this test data point forward? That's ill-defined without further assumptions. So this is an extrapolation, but without further assumptions, it's ill-defined. So under what conditions may this actually work? So as a big picture, there's at least two main conditions under which this could at least potentially work. The first one is that the training and test data distributions, they appear different, but they are actually not so different from the model's perspective. So for example, the message passing graph neural network, what it actually sees about the graph are these computation trees, the local neighborhood trees. So if the small and the large graph have the same distribution of these trees, then what the neural network sees looks pretty much the same. So at least up to the node embeddings, it may actually do a very good job and be able to learn it well. And a similar thing can be shown for spectral graph neural networks that work with a graph Laplacian. If the graphs are coming from the same topological space or from the same graph owner, so under some conditions on the filters, you can show that actually you get the size generalization. But this is, of course, not always the case. So for example, if you look at Erdős-Rényi graphs and you make them larger, the degrees change. And once the degrees are larger, for example, these computation trees no longer look the same. So there are cases where this actually doesn't hold. So what could we do in this case? In this case, we have to somehow guide or restrict the model more via prior knowledge to make it less ill-defined. So to do this, what we actually have to understand is these inductive biases. What does the model actually learn? And then use that to restrict or guide the model accordingly. So let me just show you one example of how you could potentially approach this and formalize this. And to get a hold on this, because it's a complicated problem to understand what the model actually will learn, even within distribution and then even more outside of the distribution. So one approach could be to look again at our graph neural network as this collection, like arrangement of learnable blocks. So let's look at one of those blocks first, and then try to see if we understand the behavior of one of those blocks, then we understand the behavior of the full thing. So here I will actually make the block even smaller. The block is that aggregation function. Let's look at one of the nonlinear functions inside. That is our fully connected neural network with a ReLU activation function. So what happens if this fully connected neural network gets as input an input vector, so it gets these node representations as input vector that it hasn't encountered during the training process. So if you look at it from the perspective of that neural network, now we're in a Euclidean space, it's easier. Let's say we're observing this training data in a bounded domain. If you go away from that bounded region, your neural network will just extrapolate directionally linear. So this is not so surprising given that these ReLUs are piecewise linear functions, but the thing is we're still using gradient-based optimization. So where exactly these are is not directly obvious. So we can formalize this via the neural tangent kernel framework to actually prove a result that this is the case. So what it means is that all our neural network, like all the presumably nonlinear parts of our neural network, become linear if we go away from our training data. So if we look at extrapolation. And this will happen if the degrees are larger, for example, then the inputs to the nonlinear functions in our network, the FNNs will change. So let's look at what this means for the full graph neural network at one example. So let's look at mimicking shortest path. So learning shortest path. In this case, what we do is in each iteration, we update the state of the node, which is the distance to the source node, by looking at the neighbor's distance to the source and the distance to the neighbor DHV. And we're minimizing over the neighbors. So what this means is our aggregation function has to implement an addition and the minimum over the neighbors. So this is possible if our FNN, our mini neural network inside, is a nonlinear function. But once it becomes linear, the entire graph neural network becomes a linear function, and this is no longer possible. And this is indeed what we see empirically too. So if we look at these plots, on the left-hand side, look at the red bars, you see training and test distribution are the same, the error is low. Once the training and test are different, the error is very high because this neural network becomes a linear function. Now, if we would replace the sum by a maximum pooling, which actually people have found in practice works better, then we no longer run into this problem, because even if this FNN is a linear function, we can implement shortest path. So this means even the nonlinearities, the way we do the pooling and we define the nonlinearities, matters for the behavior out of distribution, even more than within. So whether I use ReLU or sigmoid, what I actually use here for the pooling. So with that, let me just, in the last minute, pop up some open question, and let me focus on maybe the most challenging one. Is to understand what a neural network learns depends on the structure of the model, the invariances, the architecture, the optimization process, and the data geometry, all of this. And to understand the interplay of all of them is very challenging. Like, how does the structure actually affect the optimization dynamics? What does it mean for the actual function that we get out? What is the expressive power of this? And what does it mean for our sample complexities and the type of data we need to identify the right functions? So understanding all of these needs a lot more work and formalization in analyzing these methods. Thank you.
Thank you very much, Stefanie, for very interesting and thought-provoking talk. So the question can be addressed as Stefanie directly via Discord chat. Thank you very much once again.
Thank you.
So thank you